So we're going to continue working with angle relationships in circles. Remember, the key thing that we talked about earlier was to look for where the vertex is. So we're going to look at different diagrams. So you're going to see secants, chords, tangents create more angles. But again, the key thing is where is the vertex? So even though this is not what we call an inscribed angle because it's not made from two chords or two secants, now we have an angle that's created by a secant and a tangent line. The vertex is still on the circle, so it still has the exact same relationship. So if a tangent and a secant, or tangent and a chord, intersect a circle, oh, that's circle, at a point on the circle, then the measure of the created angle is 1/2 the measure of the intercepted arc. So it has the exact same relationship as the inscribed angle. So the measure of angle ABC, is going to be 1/2 of the arc that it intercepts. And you'll see it intercepts this arc from A to B, right? That's the part that's kind of inside the mouth of that angle. Okay, so if we take a look at example 1, here's where things might look a little confusing. We have a whole bunch of angles, we have a whole bunch of lines, chords, secants, whatever, right? Tangents hitting the circle. Make sure you still just bring it back to what individual angles are we looking at. We're going to assume anything that looks like a tangent is a tangent. So a point of tangency would be F and a point of tangency would be G. Okay, we're going to look for two things. Let's look for the measure of angle EFH. And let's also look for the measure of angle HFG. Okay, so let's start by looking for the measure of angle EFH. So just like before, look at where the vertex is. And F is on the circumference of the circle, which means that angle should be 1/2 of whatever its intercepted arc is. So if we follow the vertex out to E and out to H, you should see that the intercepted arc is this 130 degrees. So pretty straightforward. The measure of angle EFH should be 1/2 of that arc, FH. So we're just going to take 1/2 of 130. So that should give us 65 degrees. So if you look at part B, then we're trying to find the measure of angle HFG. So this might be a little more involved, but once again, where is that angle, the vertex of that angle? It's on the circle. So we know that this angle, which happens to be an inscribed angle that we talked about in the last lesson, is going to be 1/2 of its intercepted arc. And this time the arc goes from H to G. But the big question is, what does that arc measure? Because we don't have anything written there. So think about it. What do you think we're going to do to find that missing arc measure? Well, remember, a full circle is 360 degrees, and we have a linear pair. So if I called this angle FGI, for example, how do I find the measure of angle FGI? Well, a linear pair adds up to 180, so 180 minus 122 gives me that angle measure, which should be 58 degrees. And then remember, the angle G here has a vertex on the circle, so that means it's 1/2 of the intercepted arc, FG. So if I double 58, I know that that arc from F to G is 116 degrees. Right. So then I can use the 116, the 130 to find HG because I know a full circle is 360. I'm going to do 360 minus 130 minus 116. So that arc is 114 degrees, which means coming back to that original inscribed angle theorem, the measure of angle HFG is 1/2 of 114, which is 57 degrees. Okay, so we just want to be okay with looking at multiple relationships, just adding in the new angle relationships we're learning. We're going to do one more in this video, and that'll be it. We'll finish the rest in class. So the second theorem now deals with an angle with a vertex, notice now, in the interior of the circle. Make sure you notice this is not necessarily the center. It could be the center, but it doesn't have to be, so we don't want to assume anything. So this theorem says if two secants or chords intersect in the interior of a circle, then the measure of each angle formed is 1/2 the sum of the intercepted arcs. Okay, so again, we don't want to assume that E is in the center. It could be if BC and DA happen to be diameters, but if they're not, that's okay, because what we're going to do is look at the intercepted arcs. So if we focus on angle 1 here, you'll notice two things. There's actually vertical angles, so angle 1 is congruent to angle CED as well. And we're going to use those two intercepted arcs on the two sides of those vertical angles. So the measure of angle 1 is going to equal 1/2 the sum of the two intercepted arcs opposite of angle 1. So it's going to be the measure of arc AB plus the measure of arc CD. Alternatively, if we want to find, let's say, measure of angle 2, which is AEC that I just wrote in there, that's vertical to angle DEB. So then we'd be looking at these arcs instead, AC and BD. So the measure of angle 2 would be 1/2 the measure of arc AC plus the measure of arc BD. Okay, so that's our second theorem. So if you take a look at example 2, I want to find the measure of angle AEB. So first identify where is angle AEB. AEB is this big one right here. So then what are the intercepted arcs that go with it? Well, hopefully you're seeing definitely AB, but then you also want to see, okay, what's vertical to AEB? Well, that's here on the bottom, DEC, and use the arc that corresponds to DEC as well. So I'm going to use that information to set up my equation. So the measure of angle AEB is going to equal 1/2 of the arc measure of AB plus the measure of arc DC, and then just plug it all in. These theorems don't have any nice names to go with them, so remember, if you're using them in a proof, just abbreviate, summarize as well as you can. Okay, so just make sure you have your PEMDAS done correctly. 113 plus 139, that's going to give us 252, and then divide that by 2 to get 126. All right, and remember that angle is not a central angle because it's not the center. It's just somewhere in the interior, right? Unless you specifically see that we have a dot in the middle, or you're told that these are all diameters, or use the name of the circle, don't assume it's a center. Okay, we'll wrap this up in class looking at one more theorem and go over any questions. Thanks for listening.